Welcome to Maths with EJD. We continue with spectral analysis as we look at Fourier theory basics. Of course, we've had a couple of videos talking about spectral analysis, how it is connected to Fourier series, because it all involves talking about sinusoids, harmonics, and all of that. So here, again, we are revisiting the idea of Fourier series. So we'll look at Fourier theory basics. Interestingly, I have a playlist on Fourier series which you can check to get the mathematical background of Fourier series. Here, I'll be talking more about the theory, and of course, I'll be showing you some codes to implement some things in Fourier series. So Fourier theory basics is what we're considering, and in the introduction, we see the motivation for Fourier series, right? For Fourier theory. First of all, one of the motivations is that signals often contain multiple frequency components. We already understand that spectral analysis involves translating a signal or a data set from the time domain into the frequency domain. So we can see the frequency compositions of the data set in that realm. Okay, so Fourier theory is motivated by the fact that signals often contain multiple frequency components, and then decomposition into sinusoids simplifies analysis and filtering. And that is where Fourier series comes in. Fourier series helps to translate a function in the time domain into a function in the frequency domain. And then most of the times we have, in fact, generally we have the function broken down into sinusoids, talking about sines and cosines. So the composition into sinusoids simplifies analysis and filtering. In talking about the applications of Fourier theory, it is good. It is used for audio processing, like as in equalizers, sound equalizers, and it is also good for noise removal. For instance, I use a microphone that is a not that cancels noise, so I can imagine that Fourier theory is applied in that kind of situation, and it is good for image processing, for JPEG compression and filtering. It is good for communications like modulation. I mean, radio frequencies and all that. Like FM, for instance, in radio presentation is frequency modulation, right? So it filters out unnecessary frequency, so you can get. In fact, the what FM is called in Yoruba language in Nigeria is something to the effect of something that brings a sound that makes a sound boom, something like that, because you are getting as pure a frequency as possible from the radio. So in communications, you have modulation, you have OFDM, and then you have scientific computing to like solving PDEs. So I've used that. I think I attacked Fourier series from the angle of solving ODEs a lot in the previous playlist on Fourier series. So what is the core idea of Fourier theory? So any signal can be expressed as a combination of sinusoids. That's the core idea. So you can have any signal, any data set, any function, any time series. You can break it down into sines and cosines. Those are sinusoids. So periodic signal. So you can have periodic signals like for Fourier series. So for periodic signals, you use Fourier series. For aperiodic signals, you use Fourier transforms. And for discrete sequences, you have DFT and FFT. DFT, I think, is discrete Fourier transform, and FFT is fast Fourier transform. So we'll be exploring all of these concepts in this video. Okay, let's go for Fourier series, talking about periodic signals now. So first of all, the definition in trigonometric form for a period f of t, for a period f of t, I think I want to show everything at once. So for a period f of t, which is equal to a naught, a period f of t, which is equal to a naught, summation from n equals 1 to infinity, an cos n omega naught t plus bn sin n omega naught t. So for any function f of t with period t, you can actually express it this way in Fourier form, where omega naught is 2 pi over t, right? And then, of course, 2 pi over t is exactly the same thing as 2 pi over 2 pi f, because f is the same thing as 1 over t. So frequency is the inverse of period, just like period is inverse of frequency. Then you have a naught, that's the first coefficient that you have here. That is 1 over the period, then multiplied by the integral of f of t dt over the period. And then you have an, the a's. So you have an, which is 2 over t integral over the period of f of t cos n omega naught t dt. And then you have bn, which is 2 over t integral f of t sin n omega naught t dt. So that's basically what the whole Fourier thing is about. So you see, you transform a function, it's a function in time domain f of t into sinusoids, into cosines and sines, and that's talking about frequency. So you can see some kind of modulations and all of that. So these coefficients represent the amplitude of the sinusoidal components. So for instance, an is the amplitude of the cos component, while Bn is the amplitude of the sine component. That is what that is about. Okay, so that's talking about periodic signals. Now let's talk about Fourier series. Now, what we have seen before is Fourier series in the trigonometric form. How about Fourier series in exponential form? This is exactly what it is. You have f of t equals summation from n equals infinity to infinity, cn e raised power j n omega naught t, and cn is 1 over t integral over the period t f of t e raised power minus j n omega naught t dt, like that. Now, you know, there are times that working with exponents is easier than working with trigonometry. We see that a lot in a field like complex analysis, right? So sometimes when you represent something like cos theta plus j sine theta as e raised power j theta, you know, that it's easier to handle e raised power j theta than handling the whole thing, the cos theta plus j sine theta, right? So, and then we talk about some properties of Fourier series. So one of the properties is linearity. So that what that simply tells us that is that the Fourier series or the Fourier transform of the sum of a function is the sum of the Fourier transforms of the individual functions. That's the idea of linearity. So it means that yeah. So if you have a f of t plus b g of t, it's the same thing as a multiplied by cn, which is the Fourier transform of f of t, plus b multiplied by dn, where dn is the Fourier transform of g of t. So it's linear like that. And then you can take it back also. Then you have the time shift. So if you have a time shift, say f t minus t naught. So the function of t minus t naught can be expressed as the exponential from e raised power minus j n omega naught t naught multiplied by cn. Then you have the Parseval's theorem, which is 1 over period integral over the period of f of t squared dt. And that is equal to summation from negative infinity to infinity of the square of cn. Of course, you remember, yeah, square of cn, like that. And then let's look at some Fourier approximation using Python, right? So, I mean, I've always done Python codes for these things. Let me clear output so we can start afresh. Okay. So Fourier series approximation here now. So of course you can go through this code and see we need NumPy for numerical Python. So we see that we need that for things like linspace, and to get pi we need it from NumPy also. And then of course yeah, this to get sine and cosine and even sine like SIGN and SIN sine and all that, you need to get them from NumPy. And then we have Matplotlib for visualization, and then we have scipy.fft. So it is from scipy, the scipy library, which is scientific Python. It is for me to get the fast Fourier transform. And from there, you can import fast Fourier transform frequency, and fast Fourier transform shifts, like that. So you declare the period. This is 2 pi, that's 360 degrees, but it's 2 pi in radian. And you have t. So you're saying from 0 to t, you divide that into 1,000 equal parts, and then you get the signal. And usually we know that signal is either a data set you have or a formula that represents a time series. So here we have a square wave approximation here, which is np sine t, you know, and then we have Fourier series coefficient. We say n is 10, then we approximate np dot zeros like t and all this. So you can study this code. So in short, when we run this, I think yeah, we plot the signal and the approximation in lines 18 and 19. And then, you know, we label the axis as usual. So you can go through the code and see what it looks like. Okay, so I run this. Of course, when you're running Google Colab for the first time, it takes a bit of time. So you see what this is like. So this is Fourier series approximation of a square wave. So the original wave is in blue. So you can see that's more like a perfect square. And then you have the Fourier series approximation for n equals 10. Okay, so n equals 10 is the, you know, talking about the number of intervals or so for for the counting. for harmonics, right? So you see it's not as square as that, but then it's the more you increase that. In fact, well, we can look at multiple approximations here now. So I mean, this is just a continuation of what we have done up there. So when you come here, for instance, and you want to do multiple, so in this case, we have a list of harmonics. Of course, the first line is to dimension the figures you want to plot. Then you have harmonics list. So you have, of course, harmonics are multiples of the basic frequency F naught. Okay, so harmonics here we have 1, 3, 10, 50. So 1 times the basic frequency, 3 F naught, 10 F naught, 50 F naught. That's what that means. So we now say for I and N in enumerate harmonics list. So we want to iterate over this harmonic list, and then we'll do the same plot like we did before, like that. So that's for any range 1 to N squared up to 2. Then we approximate plus equals 4 over pi, 4 over pi. That's talking about, I think that should be about the period now, times 1 over np sine nt. So then we run, so for all this, so these two fours now is actually a kind of nested for loop. We have not done, okay, this is another thing entirely. So if you want to know more about Python, so you can check out my playlist on Python basics with EJD. So you can understand how functions are declared, control flows, and things like that. So then you can study this code better. So if I run this, it gives us 4 plots side by side. So for the first one, we have the blue, which is the original, and we have for one harmonic. So you have something like a sine curve like that, starting from the origin. Then when you have 3 harmonics, you tend to have, let me see, does it have something to do with the number of bumps here? Like this is 1, 2, 3 in between, apart from the extremes. So for 3 harmonics, we have this 1, 2, 3, 4, 5. Interesting. Up here, down here again, 1, 2, 3, 4, 5. Let me see if it is a regular pattern everywhere. Okay, so that's for n equals 3. For when you have 10 harmonics, so you have, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, it doesn't really, maybe if I follow it more, I can understand the pattern it follows. So I don't really see the pattern here. So when it was 3, we had 5. Now it's 10 and we have 18. So I don't see the pattern. So then when you have 50 harmonics, so things become very closely close together, right? As you can see here. Okay, so let's talk about Fourier transform for aperiodic signals. So don't forget, you use Fourier series for periodic signals and you use Fourier transform for aperiodic signals, right? So let's talk about continuous time Fourier transform, CTFT. So we have a forward transform that is x of omega equals integral from negative infinity to infinity of x of t e raised to minus j omega t dt. And for the inverse transform, we have x of t now. So it means if you invert this, you get this. If you take the inverse of this, you go back to the original transform. So now this is x of t. So it means if you want to retrieve this x of t, so this is what you get. To retrieve the x of w, this is what you get. So 1 is an inverse of the order. So x of t is 1 over 2 pi integral from minus infinity to infinity of x omega e raised to j omega t d omega, actually. So talking about properties of Fourier transform now. So the properties we saw before were for Fourier series. Yeah. So here we talk about Fourier transform in this situation. So again, we have linearity. The fact that a times x of t plus b times y of t it goes to a of the Fourier transform of x of t plus b times the Fourier transform of y of t, which is y of omega, right? Then you can also talk about time shift where you have x of t minus theta naught, minus t naught going to e raised to minus j omega t naught times the Fourier transform of the original x of t. Then you have frequency shift also where you have e raised to j omega naught tx of t, and that can go back and forth to x omega minus omega naught. Then you can also scale. You have scaling. So you have x of at can go to 1 over absolute value of a. Then the Fourier transform of the Fourier transform of this now we have x of omega divided by a. So what you should have had as x of omega. So anyway, there's omega in the normal x of omega. You put omega divided by a because we have a scaling thing going on there. Then there's also convolution. So I think I talked about convolution in the Fourier series I talked about the other time. I also have some Python codes attached to those. So for the convolution, you have x of t times h of t. That goes to x of w, h of w. That's so the if you are multiplying two functions, x of t and h of t, so their Fourier transform is the product of their individual Fourier transforms, right? Then you also have the Parseval's theorem like before. Integral of x of t squared dt is equal to 1 over 2 pi integral x of omega squared d omega. That's the square of the Fourier transform, integrated with respect to with omega, and then divided by 2 pi. That's what that translates to technically. So to give an example of this now, talking about proper Fourier transform. So we have this Gaussian signal. Okay, we have Gaussian signal. So here, of course, we have t from -5 to 5 divided in 1000 steps. Then we have x, which is e raised to power minus t squared. Of course, that's the whole idea of Gaussian. So e raised to power minus x squared. That is the Gaussian function. And then we also have the function from -5 to 5 also divided over that. And then we take the fast Fourier transform like this. So you have x np.fft shift fftx, and then you get the frequency also. Then at the end of the day, you plot t by x, right? So all these t and x, you plot them. Then you also go ahead here and plot a frequency by the absolute value of x and all that. So you get like two plots around here. So you look at the code properly. So you get the Gaussian signal here, and then you get the Fourier transform right here. So in the time domain, you get the Gaussian signal. In the frequency domain, you get the Fourier transform. And that's what it looks like. Now let's talk about discrete time Fourier transform, DTFT. So for discrete time signal, so here now, well, we've been talking about continuous functions, whether periodic or aperiodic. But here now, what if instead of having a continuous function, you have jumps like from 1 to 2, you don't take care of all the 1.2, 1.3, 1.004 in between, right? So for discrete time signal, x of n, you have x e raised power j omega equals summation from minus infinity to infinity of that x of n e raised power minus j omega n, right? So here, x of e raised power j omega is periodic with period 2 pi. Okay, so that's the discrete time Fourier transform. What about discrete Fourier transform itself? So that was discrete time. How about discrete Fourier transform? In this case, we have for an endpoint sequence, so n being the number of harmonics, right? So you have x of k equals summation from 0 to n minus 1, x of n multiplied by e raised to minus j 2 pi over n kn, for k starting from 0 all the way to n minus 1. So if you have 10 harmonics, you start from 0 to 9, in the function. And then the inverse is simply x of n. The inverse is x of n equals 1 over n, summation from k equals 0 to n minus 1, x of k e raised power j 2 pi over n, kn, like that. How you know it's inverse is that you see this minus here, it just comes in and becomes plus. Because we're dealing with discrete stuff. So we can have a very simple DFT example. If you import numpy as np, right, and then you declare x as np.array. So you create an array 1, 2, 3, 4. Then you can get the Fourier transform of that. So you just say np.fft.fft of these things you have declared now. And then you can now print the DFT, which is now going to be this. You see, the first array is x, but the DFT is now big X, right? So if you run this now, you get these values. 10 plus 0, 10 plus 0, then for one, which I think I did this example when I taught Fourier series, right? So when you have actual numbers and you transform them to into discrete Fourier transform. So 1 is 10 plus 0j, that's simply 10 in short. Then 2 is minus 2 plus 2j, then 3 is minus 2 plus 0j, 4 is minus 2 minus 2j. So if you check that playlist, you find how we can actually get to do this. There's a way to go about it. There's formula for it. Then let's talk about sinusoidal signal using FFT now. So in this case, we have we have the sampling frequency 1000. So the period now will be 1 over sampling frequency. The number of harmonics is 1024. T is NP in range n multiplied by t. So you have a range of value n. So this n here, right? And then you have frequency 1, frequency 2, that's 50 and 120. So we have two different frequencies we want to use on these things. And then we have x defined as sine of 2 pi ft plus 0.5 sine of 2 pi f2t. So f1t and f2t like that. So of course, we can't get we can only get sine from numpy. That's why we have np dot sine. And we can only get pi from numpy. That's why we also have np dot pi like that. Then you can now come for the fast Fourier frequency. So you have x times FFT of x. So big X is FFT of the x that you have here, the signal, or in the other case, maybe data set. Then for the frequency, you have FFT frequency n, that 1024 by the period 1 over fs. Then you can then go ahead and do your plotting. So here we are plotting t against x. In this other case, you're plotting frequency against absolute value of that x again. So if you run this, see what you get. So you have in the time domain, you have this signal all over the place, and then the frequency domain. So you can see this whole confusing signal has been narrowed down to so you just see two main frequencies. Do you see the frequency has two peaks, two magnitudes like this. So that's why breaking things down into frequency domain can be quite helpful sometimes. So now this whole thing that makes almost no sense, maybe, comes here, and then you can just see two frequencies standing out. So let's talk about spectral resolution effect. Okay, for spectral resolution effect now, we have of course, this is to dimension the graph. Then we take some values of harmonics for 256, 51 to 1024, 2048, and for AX and N. Then we zip the axis and the values together, and then we take T over a range n. So whatever n you pick, right? So this for already tells us we are looping over those values that have been zipped together. So we take them in pairs like that and plug them into the signal. So we have the signal 2n just like before, for definitely. So x times FFT. So the only thing is that you're going to have it over the whole range. And then if you run this now, you get different figures. So for 256, see what you get. For 512, see what you get. So this is just an extension of what we did previously. For 1024, see what you get. And for 2048, see what you get. All right. So let's go ahead and talk about fast Fourier transform proper. So far we talked about discrete Fourier transform. So for fast Fourier transform, it is an efficient algorithm to compute the discrete Fourier transform. So you see, discrete Fourier transform and fast Fourier transform are actually close. The only difference is that fast Fourier transform is actually an efficient algorithm to compute the same discrete Fourier transform we've been computing so far, and then it reduces the complexity from a quadratic complexity O(n) squared to O(n) log n, right? So for practical considerations now, we have zero padding, which improves frequency resolution, and we have windowing, which reduces spectral leakage. I think in one of the previous videos, I talked about windowing and the different types of windowing, like Hanning, and all of that. So let's look at FFT example for a two-tone signal, right? You have a two-tone signal. Of course, you have the sampling frequency, you have the time range from 0 to 1 divided into 1 over 1000 equal portions, right? Then you have the signal itself, the same signal like before. So two frequency signals summed up together, and then n gives you the length of the signal. Okay, n gives the length of the signal. Then you have the frequency of the signal using FFT.FFT frec, and then you have x, which is n.FFT.FFT of the signal. And then we just go ahead and, of course, this is you dimensioning the figure, and then you plot frequency against absolute value of x divided by n. So you have FFT of two-tone signal, right? So if you run this, so you get FFT of two-tone signal. So I mean, two-tone is probably why we have two frequencies standing out like that. Those amplitudes, shooting out above the zero. That is what you find in the most part. So for the summary, right? What have we been talking about? So if you talk about Fourier series, it's good for continuous time and periodic signal type. Then the spectrum, you have discrete harmonics. For Fourier transform, it's also good for continuous time, but for aperiodic signal. So for Fourier series for periodic signal, Fourier transform for aperiodic signal, and it's you have it, the spectrum is continuous. And then you have discrete time Fourier transform. So of course, the domain, of course, as the name implies, is discrete time. The signal type is infinite, and the spectrum is continuous periodic. Then you have discrete Fourier transform, of course, also in discrete time, and the signal type is finite, and the spectrum is discrete, right? It's countable. Then you have fast Fourier transform, which is an algorithm that is finite, and of course, the spectrum is discrete and it's quite efficient. So if you want to consider advanced topics of Fourier for Fourier theory, you can be looking at short-time Fourier transform, wavelet transform, discrete cosine transform, 2D Fourier transform for images. I think in subsequent videos, you're going to interact with some of these other ones. So watch out for that. So with this, I come to the end of this video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel free to let me know. And if you have subscribed already, thank you so much. If you haven't, you know you're missing out already. So go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can even take it further. Click on join to become a member of this channel, and you get some special privileges, which you'll see when you click on join. And of course, ultimately, click like, share, comment, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.